Now energy is not a vector, it's a scalar. For instance, kinetic energy. Kinetic energy is 1/2 mv squared. That has no direction because you're squaring the velocity. And for sure, if an object has a certain amount of kinetic energy and it hits a solid surface and bounces back, it exchanges momentum. There's a big change of momentum in this direction. But it has the same kinetic energy. It hasn't given any energy to this object. Now you can say, well, yeah, because this object is going to recoil, but if this object is big, like the Earth, we showed that kinetic energy it gives it is negligible. Remember, 10 to the minus 20 joules. So energy is a scalar. It's just like apples. You have 5 apples, I give you 2 more, you got 7. This has 5 joules of kinetic energy, I give it 2 more, it has 7 joules of kinetic energy. However, how you do work, if we change the energy in a system by putting work in, then direction really matters because work is equal to force dot displacement. Let's see what this means. Let's say there's a car and I push it with a force in this direction as it's moving in this direction. Okay, let's not look at friction. Imagine what will happen. I'm putting force on it and it's moving, it's going to speed up, its kinetic energy is increasing. Now what if the force I put on it is in this direction, but it's moving in that direction? Now as it approaches me, I slow it down and take its kinetic energy away. And so this would be a positive change of kinetic energy, this would be a negative change of kinetic energy. So really, it's not just force times distance, it's force times distance in the same direction. If it's going the other way, it's a negative. Similarly, what if I have a block on a frictionless surface and I put a force on it in this direction as it's moving along on the frictionless surface? Do I change its energy at all? I put no force on it, I'm not speeding it up, right? All I'm doing is by lifting it up, I'm lowering the normal force. But this force itself, force of Pete, does not change the energy. However, if this were not sliding, but rather this was at a cliffside, and I pulled it hard enough so that it moved upward, and let's say this force was equal to the force of gravity, so it wasn't speeding up. I'm just compensating for gravity as I push on it upwards. Then we have force times delta H is work because the force and the change in displacement are in the same direction. And so I can say then work in is equal to force of P times delta H in the same direction. And the force of P is the same as gravity. And then I have delta H. And what do I have there? That's just the potential energy that I'm giving it. So here, not only have I shown that I increase the energy, but I've shown that if you push something upward, the work you put in is equal to its change in potential energy. So we see that if they're parallel, the energy of the object is going to change. If they're perpendicular, such as when I'm pulling up and it's moving in this direction, the energy doesn't change. How about kinematics? Is direction important in kinematics? Well, surely. If I'm standing right here and you displace me by 1 meter, 1 meter in the positive x direction is going to have very different effects than 1 meter in the negative x direction. So displacement as well requires that we define a positive direction. I can define this as a positive x direction and this as a positive y direction. And so that goes for displacement is now a vector. We put a hat on it like this. Velocity, which is the rate of change of displacement, and acceleration, which is the time derivative of velocity. Acceleration is also the vector sum of the forces divided by the mass, and that's how these are connected. But there are 2 other kinematic variables that's important to distinguish. One is the distance or the length. I'm going to write that as an L. I don't find it in the textbook at all, but we write it as an L in this class, and speed, which is the V without the hat on it. Your textbook again does it somewhat differently, but this is how we're going to write them. So how are these different? Imagine we're looking at a map and you walk 100 meters in the positive x direction. So this would be displacement 1 is equal to 100 meters in the x direction. And then you walk 200 meters in the y direction. Okay? So what is your final displacement? We add these like vectors and we see that our final displacement is the vector sum of these, which is going to be, there's two ways to write it. We could write 100 meters in the x direction plus 200 meters in the y direction. And so that says if I start here, I'm going to end up there. But there's another way we can do it with angle and magnitude. We can say, oh, there's some angle theta, such that I know, oh, this is tangent. Tangent of theta is equal to delta x2 over delta x1, right? Because this is a right triangle. That's the adjacent side, that's the opposite side. So I can define the angle and I can define the magnitude. We square these, add them, and take the square root. So x, delta x, the magnitude, is going to be 2 squared is 4, plus 1 is 5. So it'll be 100 square root 5 meters. Theta is equal to the tangent inverse of 2. This winds up being about 63 degrees, and this winds up being 224 meters. The book makes a mistake, in my opinion, about how it defines distance. It says that the distance is the magnitude of the displacement, and they would define it as 224 meters. But that's not how we use distance. If you walked this way, and someone said, what's the distance you walked? You walked 300 meters. This, I'm sorry textbook, this is path length. It's just how far you walk. I mean, the perfect example is, you walk in a circle. What's your displacement? You're right where you started, your displacement is 0. What's the distance you walked? Well, it's 2 pi r. It's the circumference of the circle. So when we talk about distance, it's going to be path length. And how about speed? Well, speed is then the path length divided by the amount of time it took. And so, again, according to their definition, your average speed would be 0. But according to mine, your average speed would be the length of the path divided by the amount of time that you took to go that distance. Okay, so what we've seen is it's very important to recognize that forces are vectors that need to be added like them. Momenta as well. Well, energy is a scalar that the work in is a dot product of these two vectors such that it's the parallel component times the displacement. And the kinematic variables, displacement, velocity, and acceleration, also need to be recognized as vectors or added like vectors. But we have kinematic scalars as well, path length and speed, which is the rate at which you are moving on a path.